The first speaker is Zhang from MPI Leipzig. He will talk about higher order eigenvalues for graph p-Laplacians. So please, Zhang.
Okay. Thanks so much for the introduction and invitation. It's my great pleasure to give a talk in the conference. I would like to talk about higher order eigenvalues for graph p-Laplacians. Here's the outline. In the first part, I will introduce the graph p-Laplacians and discuss some basic properties for the spectrum. And in the second part, I shall present further results on the min-max eigenvalues with particular interest in the relationship between variational spectrum and multi-way Cheeger constants. And in the last part, I shall focus on the homological eigenvalues of p-Laplacian. Okay, so first let's fix some notations. We use G to denote a simple graph, and for convenience in this talk, we always assume G is undirected, unweighted, finite with no loop. We let V be the vertex side and E be the edge side of G. And the well-known graph Laplacian is defined by this formula, and its normalized eigenvalue problem can be formulated by this eigenequation. The multiplicity of the eigenvalue 0 is the number of connected components of the graph. And the second eigenvalue lambda 2 reflects how well connected the graph is. That is, the larger the lambda 2 is, the more connected the graph is. And so we may call lambda 2 the algebraic connectivity, and it is positive if and only if the graph is connected. And we say a graph G is a spectral epsilon expander if lambda 2 is larger than epsilon. Lambda 2 has a deep relation with the Cheeger constant. The Cheeger constant is a combinatorial minimization. Here the boundary of S, this term means the number of edges that cross S and its complement, and the volume of S is the sum of degrees of vertices in S, and the minimization is taken over all non-empty subsets of S of V, and we say G is a graph epsilon expander if H is larger than epsilon. A well-known result says that a graph expander is equivalent to spectral expander. And in other words, expansions approximate the spectral gap. And the famous Cheeger inequality, as shown here, is actually a quantitative version of that statement. Graph Laplacian has been widely used in diverse areas. And I think many audiences are experts in these fields, and so I won't go into detail. Let's just move to graph p-Laplacian. Okay, so let's get started with this formulation. Look at the blue parts. If p is 2, then the blue terms vanish, and we get nothing but the original graph linear Laplacian. And in fact, the p-Laplacian acting on F is 1 over p times the gradient of this p-homogeneous convex functional at F. And the eigenvalue problem for the graph p-Laplacian is to find a real number lambda and the function F satisfying this eigenequation. And we can of course rewrite it by these Lagrange equations. And the eigenvalue problem for p-Laplacian is equivalent to find the critical value and critical points of this p-Rayleigh quotient. If we regard the function f as a vector in Rn, then we can write the p-Laplacian in the metric form. Here we use the incidence metric of a graph, and phi p is a map that maps each component to its power p minus 1. And if p is 2, we get that identity. And if p is 1, I mean if p turns to 1, we can get the graph 1 Laplacian. But here we should know that phi 1 is a set value map in which we use a set value the signature function instead of the usual signature function like this. Okay, and the one-Laplacian eigenvalue problem is to find the real number lambda and the function f satisfying this intersection condition. Okay, it is a little complicated. I will explain it later. In fact, when Laplacian acting on f equals the subgradient of this total variation functional, and it is a compact convex subset in Rn. And of course, we can reformulate the one Laplacian eigenvalue problem as this differential inclusion. And to explain it clearly, we should put all these things in a general framework for a general nonlinear eigenvalue problem. Okay, let's start with this general setting. For local elliptic function, phi and psi, we say a function f is an eigenfunction and lambda is the corresponding eigenvalue of this function pair phi comma psi. If the Clark derivative of phi at f intersect with lambda times the Clark derivative of psi at f, and if we use a notational Minkowski sum, then we can rewrite this eigenvalue problem by this differential inclusion. And then we can unify the p-Laplacian eigenvalue problem in the following way. The eigenvalue problem for p-Laplacian with p larger than or equal to n can be unified into the eigenvalue problem for the function pair phi comma psi. Here phi is a p-homogeneous total variation functional, and psi is a weighted LP norm to its power p. Okay, so when are we interested in graph p-Laplacians? I will show you some motivations. Mathematically, graph p-Laplacian is a natural discretization of the continuous p-Laplacians on Euclidean domain, and it is also a natural nonlinear variant of the graph linear Laplacian matrix, and its spectrum has many relations to the properties of the graph itself. For example, its eigenpairs includes important information about the geometry and topology of the graph, like the Cheeger problem and the shortest path problem on the graphs. And moreover, a graph p-Laplacian has many applications, including the spectral clustering, data image processing problems, and unsupervised learning and semi-supervised learning. And some recent results indicate that algorithm based on graph p-Laplacians often perform better than the algorithm based on the linear Laplacian for solving the spectral clustering or the image processing problems. Okay, but in this talk, I only focus on the theoretical part. Let's go back to the one Laplacian. It is very interesting that one Laplacian is not only a set value map, but also a xenotop value map. So what do I mean by xenotop value map? That is, for any function f, one Laplacian acting f is actually a xenotop. So what is a xenotop? It is a Minkowski sum of finitely many segments. It is a projection of hypercube to a linear subspace. It is a convex polytope that all faces are centrally symmetric. All these definitions are equivalent. For convenience, so we regard the empty set and single point as xenotopes. And very interestingly, such a simple object has many relations to for example, have a plan arrangement, vector configurations, oriented matroids, and tilings, and traffic geometry. And many mathematicians made their contributions around this topic. As a special xenotop, the graphic xenotop includes many properties of graph itself. Here the graphic xenotop Z of G is defined to be the Minkowski sum of some segment of this segment with endpoints EI and EJ. Here E1, E2 up to En forms a canonical base of Rn. And we know that the volume of Z of G is the number of spanning trees of G, and the number of lattice number in G is the number of forests in G. And in fact, we have so many properties on the graphical xenotop. Okay, let's turn to the relationship between the Van Laplarian and the graphical xenotop. In fact, graph Van Laplarian is actually a graphical xenotop valued map up to some scaling factor and the translation vector. So what do I mean? I mean that Van Laplarian acting on F can be written by these formulations. It is in fact a graphical xenotop of is some subgraph GF of G. Here, GF is a subgraph defined on the vertex way, and IJ is an edge of GF if only if IJ is an edge of the graph G and Fi equals Fg, and we can reformulate it by the variant graphical xenotop with the translation to the center position. This center position is obtained by taking limits of the p-Laplacian acting on F for p tends to 1. Okay, of course, Van Laplarian can be seen as the limit of p-Laplarians. Preciously, delta 1 acting on F is the saddle limits of p-Laplarian acting on F tilde as p tends to 1 and F tilde tends to F. And if we take the limit p to 1 first and then take the limits F tilde to F, then we get a collection of all center points of the faces of the Van Laplarian acting on F. Here we use the fact that delta 1 F is actually a xenotop, and so every face is centrally symmetric, and therefore they have centers. Okay. Moreover, the limit points of eigenvalues and eigenfunctions of p-Laplarian are eigenvalues and eigenfunctions of Van Laplarian as p tends to 1. However, there exist some eigenpairs of Van Laplarian that are not limits of the p-Laplarian eigenpairs. Here, the eigenpair means a pair of eigenfunction and its corresponding eigenvalue. And in addition, we have these propositions saying that the spectrum of p-Laplarian is approximately continuous with respect to p for p from 1 to infinite. What do I mean by the approximately continuous? It means that for any positive epsilon, there is a positive delta, such that for any p prime in the delta neighborhood of p, and the spectrum of p prime Laplarian is included in the epsilon neighborhood of the spectrum of p-Laplarian. Okay, let's say the eigenvalue multiplicity. So first, the eigenspace x lambda of delta p is defined to be the collection of eigenfunctions corresponding to an eigenvalue lambda of the p-Laplarian. If p is not 0 and if lambda is not 0 and p is not 2, then this eigenspace is not linear, but it is always centrally symmetric. So we should use some nonlinear dimension to replace the linear dimensions. The question is characteristic genus is a suitable choice. And for convenience in this talk, we call it the Z2 index. Z2 index of centrally symmetric subset S in Rn is a minimal K such that there exists the continuous map from S to the unit sphere of dimension K minus 1. And we simply write this Z2 index by index of S. If S is a linear subspace, then the index of S equals to the dimension of S. And if the index of S equals K, then S contains at least K orthogonal vectors. In this talk, we don't consider zero functions, so we may assume there is not included in S. And then we can define the eigenvalue multiplicity of the eigenvalue lambda as the Z2 index of the its eigenspace corresponding to lambda. Okay, let's see some special eigenvalues. The first eigenvalue, that is the smallest eigenvalue, is always 0, and its multiplicity is the number of connected components. So from now on, we assume that G is connected. Let's say the second eigenvalue. It is a smallest positive eigenvalue. And for p larger than 1, we have this p-Laplacian version of the Cheeger inequality. And when p is 1, we get an identity relating the Euro2 constant and the second eigenvalue of the graph 1 Laplacian. And based on this very simple identities, many good algorithms are obtained for solving chip card problem have been designed, such as a nonlinear inverse power method. Okay. The next possible eigenvalue I would like to show is number 1. We know that the number 1 is not always an eigenvalue, but it has many relations with the distribution of the spectrum of p-Laplacian and the independence number of the graph. For example, we know that counting multiplicity, the number of p-Laplacian eigenvalues larger than or equal to 1 is at least alpha. The same story holds for the eigenvalues less than or equal to 1. And if G has L duplicated vertices, or the independence number alpha is larger than n over 2, then the number 1 is an eigenvalue of any p-Laplacian on graph G, and its multiplicity is at least the maximum of L minus 1 and 2 times alpha minus n. And very interestingly, if the graph has no duplicated vertices and the independent number is n over 2, then the number 1 may not be an eigenvalue. For example, the title graphs and book graphs shown like this realize the largest spectral gap from 1 for their graph Laplacian. Okay, for the 1 Laplacian case, the number 1 is always an eigenvalue, and we can prove a stronger estimate for the multiplicity of the eigenvalue 1. In fact, its multiplicity is at least independence number, and at most 2 times alpha. And we can prove a stronger version in terms of 2 relaxation of the independence number, alpha star and alpha hat. I just want to explain alpha star. Alpha star is the maximum of I plus 2 times J, such that there exists pairwise non-adjacent I vertices and J triangles. And from this inequality, you can show that the stronger variant give refinement of this inequality. For the largest eigenvalue, if p is larger than 1, then we have these properties. Number 2 to the power p minus 1 is an eigenvalue of the graph p-Laplacian if only if the graph has a bipartite components, and its multiplicity equals the number of connected bipartite components. If p is 1, then the largest eigenvalue is always the number 1, and I can show you a very strong estimate for the multiplicity of the largest eigenvalue 1 of the graph 1 Laplacian. The lower bound is again alpha star, and the upper bound is the minimization of k star and alpha hat. Here k star is a relaxation of the Euro click halving number. I won't go into detail. I just want to show you an example. Let G5 be this graph on 5 vertices, and you can check that its independence number alpha is 2, and it's realized the independent number alpha star is 3. This is because we can find a triangle and vertices that are not adjacent with the graph. So by the definition of alpha star, we can easily see that alpha star is 3. And similarly, we can prove that K star is also 3 because we can find a clique of order 3 and a clique of order 2 to cover the vertex of the graph. And I conjectured that the multiplicity of the eigenvalue 1 of 1 apparent is nothing but the alpha star. Okay. I will show some difficulties for studying the p-Laplacian eigenvalue problem. In fact, there are more eigenvalues than the number of vertices. For the 1 Laplacian case, we can prove that the number of eigenvalues are finite, and it is bounded by n to the power 4 over 4. But for every n larger than or equal to 6, we can construct a sequence of connected graph on n vertices with at least 3 times n over 2 pairwise distinct eigenvalues of the 1 apparent on the graph. For example, let's say the graph on 6 vertices. You may see that its spectrum contains 9 different eigenvalues. And in fact, if P is not 1 and not 2, we don't even know if p-Laplacian has finitely many eigenvalues, although there is a folklore conjectures for that. Actually, we cannot compute all the eigenvalues of p-Laplacians because we have no general approach and we have no algorithm to compute the higher order eigenvalues. And the reason might be that the structure of the eigenspace is actually unclear. For example, in this graph, this is a complete graph of order 3, and you can see that the eigenspace corresponding to the eigenvalue 1 of the 1 apparent is actually the union of the 6 two-dimensional quadrants in R3 as shown in this picture. So it is very complicated. It's totally nonlinear. Okay, so we may restrict ourselves to some particular cases. And in this talk, I would like to focus on particular eigenvalues, including the variational eigenvalues and the homological eigenvalues. Okay, the minimax eigenvalues, what we also call it the variational eigenvalues, is defined as follows. The case variational eigenvalues of the p-Laplacian is defined to be the minimax of the p-Rayleigh quotient. Here, the infimum is taken over all centrally symmetric subside with Z2 index at least k. And by the Lerman theory, they provide critical values for the p-Rayleigh quotient, and therefore they provide n eigenvalues of the p-Laplacian. And if lambda is a variational eigenvalue, which appears L times in the sequence of minimax eigenvalues, then its multiplicity is at least L. However, the equality doesn't hold. Here is an example. On the path graph of order 7, we can prove that 1 over 3 appears only once in the sequence of the minimax eigenvalues of the 1 applied, but its multiplicity is 2. So it's very strange. Okay. For p larger than 1, we have these basic properties. The first eigenvalue p-Laplacian is always 0, and the last variational eigenvalue is the largest eigenvalue. And the variational eigenvalues are, of course, critical values of p-Rayleigh quotient, which coincide with the spectrum of p-Laplacian. And for the one Laplacian case, we further have that the second variational eigenvalue equals the usual Cheeger constant. Okay, and but the critical values of the one Rayleigh quotient may not coincide with the spectrum of one Laplacian. And similarly, we can prove the initial bound of the impedance number involving the distribution of the minimax eigenvalues of p-Laplacian, like this. Okay, and for kinetic graph, the second minimax eigenvalue is always the smallest positive eigenvalue of p-Laplacian. And that is to say, the second minimax eigenvalue equals the second eigenvalue. And as I have shown before, the first and the last minimax eigenvalues coincide with the first and the last eigenvalues exactly. So natural question is whether the third minimax eigenvalue agrees with the third eigenvalue. And in general, has the non-variational eigenvalue problem. Can we find the eigenvalue of the p-Laplacian that is not in the sequence of minimax eigenvalues? For complete graph and p larger than 1, the answer is yes. We can find many non-variational eigenvalues on a complete graph with p larger than 1, but we don't know which one is. And on the path graph, the answer is no for the p-Laplacian with p larger than 1. Okay, so we have many related questions. For example, are there other eigenvalues between the second and the third minimax eigenvalues? And is there a graph such that both is one Laplacian and p-Laplacian have non-variational eigenvalues? And we should know that all these problems are still open in the Euclidean domain setting. That means for the continuous p-Laplacian, all the results are still open. Yeah. Okay. Let's say the monotonicity problem. It is known that these functions involving the second eigenvalue and the last eigenvalue are increasing function of p for p from 1 to infinity. So the author asked, is there a volume of the monotonicity for other eigenvalues? This question is very difficult because we don't know much more about the non-variational eigenvalues. But if we restrict ourselves from the variational eigenvalues, I can show you a complete answer to this question. So this is the first theorem for any k. The k's minimax eigenvalue of p-Laplacian is locally limited continuous with respect to p, and the function this function means 2 times lambda k of delta p to the power 1 over p times p is an increasing function with respect to p for p from 1 to infinity. And in fact, we can see more because this function is decreasing of p for p from 1 to infinity. And so we can get a relation this time in inequality that relates case minimax eigenvalue of p-Laplacian and the case variational eigenvalue of one Laplacian. And you can see that the left-hand side and the right-hand side are decreasing and increasing with respect to p. When k is 2, we can recover the refined Cheeger inequality for graph p-Laplacian. And if p is 1, we get an identity relating the Cheeger constant and the second eigenvalue of the one Laplacian. And if p is 2, we have the original Cheeger inequality on graph. I will show some applications to motivate Cheeger constant. The KV constant is defined by this formula, and a very beautiful result proposed by James Lee, always Gahan and Trevisan, says that for every graph and every natural number k, there is a KV Cheeger inequality relating the HK and the case eigenvalue of the graph Laplacian. Interestingly, combining with our monotonicity theorem we can obtain a p-Laplacian variant of this multiple Cheeger inequality. Here, the C and CP are also the universal constants. I won't go into detail. But I want to say that if we replace the subscript of the HK, I mean, if we replace K here in the low bound by, for example, the number of nodal means of eigenfunction with corresponding to lambda K, then the constant can be improved. So what do I mean by nodal means? Here's the definition of positive strong nodal means. Take a maxima connected induced subgraph of G on the vertices with positive F value. And if P is larger than 1, that F be an eigenfunction corresponding to the case variational eigenvalue of p-Laplacian, and assume that F has M strong nodal means, then the low bound can be written in this form. Here you should know that the subscript is M, not K. And if P is 1, we get a very simple inequality relating the KVT constant and the case variational eigenvalue of 1 Laplacian. Okay. Again, combining our monotonicity theorem, we can improve the lower bound. In fact, we know that in the previous variant, I mean, these two theorems, the subscript M is the number of strong nodal means of some eigenfunction corresponding to lambda K of delta P. But by our monotonicity theorem, this number M can be improved to the number of strong nodal means of any eigenfunction corresponding to the case min-max eigenvalue of any Q Laplacian for Q from 1 to P plus some sufficient small epsilon. Yeah. Okay. Another application is the relaxed KVT constant. This is definitions. It is a little complicated. The definition of HK hat is a relaxation. It is a relaxation of the KVT constant, and the definition relates to the order complex of the set pair and the including partial order. I won't go into detail. I just want to show that it's very interesting that the case min-max eigenvalue of graph 1 Laplacian coincide exactly with the relaxed KVT constant HK hat. And if K is 1 or 2 or n, and then the three quantities coincide. And if we restrict down forest graph or tree graph, okay, then the three quantities coincide exactly. I mean, the case variational eigenvalue of 1 Laplacian and the KVT constant and the modified KVT constant. Oh, yeah, they coincide on the tree graph. Okay, for any case. Let's see some examples on the complete graph of order n. If P is not 1 and not 2, then the number of eigenvalues of p-Laplacian of the order n is about n squared over 4, and those eigenvalues are listed as follows. So for n larger than or equal to 4, the complete graph of order n has so many non-variational eigenvalues. Let's look at a complete graph of order 7. It has 13 different p-Laplacian eigenvalues, and in which there are 6 non-variational p-Laplacian eigenvalues. However, it has only 4 different 1 Laplacian eigenvalues, and they are all variational eigenvalues. This is because the non-zero eigenvalues of 1 Laplacian on a complete graph of the n are in the form of n minus n over n minus 1 for I from 1 to up to n over 2. and their multiplicity are exactly 2, except the smallest positive one, that is the Cheeger constant, which has multiplicity 1 if n is even and multiplicity 2 if n is odd. And in addition, we can show that all one Laplacian eigenvalues of the complete graph are variational. Okay, the next example, the path graph. For p larger than 1, the path graph of order n has only variational eigenvalues. But if we look at the one Laplacian, then the path graph of order n with n larger than or equal to 6 has non-variational eigenvalues. Again, let's see the path graph of order 7. Its spectrum is listed here, and its variational eigenvalues are listed as here. And you can see that 1/2 is an eigenvalue of the one Laplacian on this graph, but it is not a variational eigenvalue. And another strange phenomenon that you see that 1/3 is a variational eigenvalue, but it appears only once in the sequence of the variational eigenvalues. However, its multiplicity is 2. Okay. So as you can see, things change from one p-Laplacian to one Laplacian. So natural question is that for a given graph G, how to determine whether its p-Laplacian has non-variational eigenvalues? Of course, it is still open questions, and mathematicians tried to compute all the eigenvalues of for at least n+1 different eigenvalues of p-Laplacian on particular graphs, and they also tried to establish better theory for the no-domain bounds for p-Laplacian with p=1, and for one Laplacian by just taking limits. But we know that some one Laplacian eigenpairs are not the limits of p-Laplacian eigenpairs. So a natural question is, which one Laplacian eigenpairs can be the limits of p-Laplacian eigenpairs? It may relate to the stability of eigenvalues of p-Laplacian with respect to p. And so let's say the homological eigenvalues. Basically, homological eigenvalues are obtained by considering the values of p-Rayleigh quotient, where locally there is a change in the homology group for a sublevel set. And formally, lambda is the homological eigenvalue of p-Laplacian if lambda is the homological critical value of the p-Rayleigh quotient. So what do I mean by critical homological critical value? Homological critical value was introduced in the study of precision homology. And here's the definitions. Number C is homological regular value of function f if there is a positive epsilon, and for each pair of real numbers is smaller than b on the interval c minus epsilon to c plus epsilon. The equilibrium from the sublevel set at level A to the sublevel set at level B induces isomorphism on all homology groups, and a real number that is not homological regular is called the homological critical. Okay, we can prove that all variational eigenvalues of p-Laplacian are homological eigenvalues of p-Laplacian, and they are critical values of p-Rayleigh quotient, and they are all included in the spectrum of p-Laplacian. I will show you the mean theorem here. For any isolated homological eigenvalue lambda of delta p, and for any positive epsilon, there is a positive delta such that for any q in the delta neighborhood of p, there exists the q Laplacian eigenvalue in the epsilon neighborhood of the p Laplacian eigenvalue lambda, such as the q Laplacian eigenvalue is a homological eigenvalue, and it satisfies this local monotonicity property like this. That is to say, homological eigenvalues are stable and satisfy the local monotonicity with respect to p. Okay. So let's say the last two examples. For example, in the graph on 6 vertices, as you can see, the graph has only 4 different one Laplacian eigenvalues, which are 0, 2/5, and 5/7, and eigenvalue 1. The eigenvalue 1 has multiplicity 3, and we can show that 5/9 is the third eigenvalue, but it is not the third variational eigenvalue. So we can see that the third eigenvalue, is not the third variational eigenvalue. And moreover, 5/9 is the homological eigenvalue. And so by the stability of the homological eigenvalue, we know that for any p larger than or equal to 1 and less than 1 plus a small delta, the p-Laplacian on this graph has a homological eigenvalue near 5/9, which is not a variational eigenvalue. Okay. The last example, again, this graph on 5 vertices, we can show that 1/2 is not a homological eigenvalue. Okay, so let's go back to the monotonicity problem. Does the monotonicity holds for this function with respect to p? We give a classification of the spectrum p-Laplacian to answer it. If we restrict on the variational eigenvalues, then these eigenvalues are locally ellipses continuous, and they are closed and taking limits. I mean that the limits of variational eigenvalues with respect to p are also variational eigenvalues. And the variational eigenvalues satisfy the global monotonicity property of this function. And if we look at the homological eigenvalues, then they are stable, but they are open. In fact, they are not closed and taking limits. That means the limits of homological eigenvalues of p-Laplacian with respect to p are not always homological eigenvalues. But the homological eigenvalues satisfy the local monotonicity of this function for some p. Okay. And the whole eigenvalue, the whole spectrum of p-Laplacian is semi-continuous, and of course they are closed and taking limits, but in general it has no monotonicity. Okay, so in summary, the graph 1 Laplacian can be seen as a combinatorial Laplacian, and because we have the following properties, let me show you. The first one is the second eigenvalue. I mean the first non-zero eigenvalue of 1 Laplacian equals to the Cheeger constant, and the variational eigenvalues of 1 Laplacian coincide exactly with the modified Cheeger constant HK hat, and they approximate the original Cheeger constant HK. And the multiplicity of the eigenvalue 1 has deep relation with the independence number alpha and the Cliff-Coupling number kappa on the graph. And the multiplicity of the second eigenvalue lambda 2 of the 1 Laplacian has much relation with the number of Cheeger sides. Okay, and the 1 Laplacian itself can be also seen as a graphical xenotop valued map. And moreover, homological eigenvalues are closely to the order complex or related to the graph itself. Okay. So our slogan here, p-Laplacian can be seen as an extrapolation between the linear and the combinatorial Laplacian. This is because the p-Laplacian for p larger than 1 and smaller than 2 can be regarded as a nonlinear evolution from the 2 Laplacian, that is the graph Laplacian, to the 1 Laplacian, that is a combinatorial Laplace operator. Okay, so this talk is mainly based on the 2 preprints, and here are some reference related to this talk. Okay, I think I can stop here. Thank you very much for your attention. Okay.
Okay, thank you so much for this very nice talk with so many stunning results and so many open problems. Are there, yes, are there any questions or comments?
Thanks for the nice talk. I have a question, and we know that the one Laplacian in graphs can be extended to the such as Hodge Laplacian on simple complex. So the same can the p-Laplacian be extended by a similar way?
I don't think so, because graph Laplacian has no simple complex structure. It is a totally nonlinear nonlinear version of the Laplacian operator, but it has no polyhedron structure. I think if we want to relate the Laplacian type operator to simple complex, like Hodge Laplacian, the eigenspace should be at least piecewise linear, I think.
Okay. Okay, thank you. And I have a little question about your maybe first page or in the beginning of the slide. You require the graph without loops, but so you mean self loops or
you mean this?
Yes, because I see you performed many examples on for the complete graph, and they will have loops. So
sorry. With self loops.
Oh, okay. Thank you.
More questions? Maybe I have one. So you're talking about you're taking limit as p tends to 1. So if you take the limits of variational eigenvalues of p-Laplacians with p larger than 1, will they converge to still variational eigenvalues of 1 Laplacian?
Yes. Because variational eigenvalues of p-Laplacians are Lipschitz continuous with the 2p for p from 1 to infinity.
It's Lipschitz. Okay.
Yeah, Lipschitz continuous.
But you said you have examples that the multiplicity can decrease, right?
Yes. It's very strange.
I see.
Yes, many things change from linear to nonlinear.
Okay, thanks.
Yeah.
Any more questions? Okay, so if it's not the case, let's thank Zhang Dong again for this very nice talk. Thank you very much.
Thank you, Professor. Thank you.